Welcome to Spring LIB.
Okay, so we're doing chapter 29, problem 61. In this problem, we have a metal circuit here, and we have a bar that completes the circuit, and we say it's moving to the right, but it's all in a magnetic field that is into the page. It also tells us that the length of the bar is big L, and that the current through this is counterclockwise. Okay, so for part A here, we want to find an expression for the force on the bar. So we want to find magnetic force. So first of all, using the right hand rule, we know that the direction of this is going to be the current across B, right? So the current at the bar is upwards. So up crossed into the page gives us in the negative x direction. So FB is in negative x direction. Cool. So we know it's going to be opposing the speed that we're already given in the positive x direction, and this magnetic force is going to be slowing us down. Cool. Good to know. So now let's work on the magnitude here. We know that the magnitude is given by ILB, because that's just the force on the bar in a constant field. So we can now simplify this a little bit, because we also know that the emotional EMF is given as BVL, which means I is BVL over R. Cool. So now let's simplify this. We have L squared B over R is our magnitude of force. And this is in the minus x direction. Cool. So now let's go to part B. So for part B, we want to figure out, as this slows down, where does it stop? How far does this go, basically, before it stops? Okay. And it also tells us that, well, we want to show that the distance it moves is x equals mv naught r over L squared B squared. Okay, so let's work on showing this. So we know that force is given by MA. So we can write A as F over M, and this is equal to L squared B over R times M. So now we can write this A as dV dt, and now let's separate some variables, and we're left with dV over V equals V squared L squared over M R dt. So let's integrate both sides here from 0 to t and V naught to V, and we're left with ln of V minus ln of V naught equals V squared L squared t over MR. Okay, so if we want to combine these two natural logs, we can then exponentiate both sides and solve for V. So if we do that, we're left with V of t, and this is going to be equal to V naught, the original starting value, times the exponential of the rest of the expression. Cool. So there's a function for V. So now V of t we can write as dx dt. So now we do that same thing, and let's separate variables again, and we see that dx is equal to V naught e to the minus b squared L squared t over mr times dt. Now we integrate both sides, and let's write this integral out over here, and we're left with V naught, or x equals V naught times minus m times r over b squared L squared and we have times e to the minus b squared L squared t over mr. And this is all evaluated from 0 to t. Okay, so if we evaluate that, we're going to see that our x of t function comes out to be mr v naught over b squared L squared times 1 minus this exponential. Cool. So we see we start at a certain position, and this is going to be monotonically decreasing with time. So we know as time goes to infinity, we limit somewhere, our speed goes to 0, which means we're going to stop somewhere. So now we can just take our stopping distance as the limit as time goes to infinity of our x of t function. So this is limit time to infinity of this. And if you see, the only place we have time is in this exponential, and it's a negative in the exponential. So if this goes to infinity, this term goes to 0, and we're left with mr v naught over L squared b squared, which is exactly what we were looking for in the beginning. Awesome, we made it there.